So part one, general rules for the design of retaining structures. And here I'm going to cover some fairly basic issues in terms of what materials we're using, how we treat groundwater, the sort of analysis that we need to do, execution is how we construct, and also what guidance documents you can turn to for detailed information about design. And again, a lot of this material is taken from the Decoding Eurocode 7 book. So if you're looking for more detail of this, that's where to go. So let's talk about materials. So the information that you need to do retaining wall design, unfortunately, is spread over a number of different documents. It's not all collected into one document. So in Eurocode 7, the current Eurocode 7, part 2 deals with ground investigation and testing. So that is where you're going to go to get information about the ground at your site, how you investigate it, how you get the parameters for it. The detail of what testing you can do, whether it's cone testing or standard penetration testing or laboratory testing, the detail of all those tests are given in separate EN ISO standards. So they're not a part of Eurocode 7 directly. They're referred to by Eurocode 7. And there's a suite of, I would think, 40, maybe even 50 different standards, each standard covering a particular type of test. And we'll look at those a little bit later. So there's a separate set of standards for geotechnical investigation testing. And these are ISO standards. So these are not just European standards. These are international standards that supposedly are available in every country in the world pretty well. This is a member of ISO. Of course, just because you've got an ISO standard doesn't mean it's followed. So for example, in America, they have American standards for geotechnical investigation and testing, and they would follow their own American standards rather than the international standard. The way that we operate in Europe is we tend to defer to the higher level standards. So in Europe, we adopt the ISO standards as European standards, and then each European country adopts the EN ISO as a national standard. So there's a hierarchy, but we're always working with the same document. So for ground properties, we're dealing with Eurocode 7 Part 2 and these EN ISO standards. For other materials, again, there is a wide range of standards available for structural steel, for reinforced concrete, timber, aluminium, you name it, there are other standards. I'm not going to cover all of those. There's way too many to cover in this particular course. I'm going to concentrate on the ones I'm showing here. So here we have on the left a pie chart showing you the contents of the current Eurocode 7 Part 2. You can see that on the left, the largest wedge are in fact the annexes. So this document has a lot of additional information given in what are called informative annexes, which is basically information that you are given that you aren't necessarily required to follow. So it's useful information, but you're not obliged to follow it. The parts of the standard that you are obliged to follow are on the right, and they're divided into the sections planning, sampling and groundwater measurement, field tests, laboratory tests, and then reporting. And those are the key elements of the current code. And a similar structure will be adopted in the second generation of Eurocodes, although in the second generation, instead of talking about the tests that you do to get parameters, we're going to talk about the parameter or the properties that you want and how to get them from tests. So we're sort of reversing the presentation of the material, changing the material so that it is very much focused on the designer's needs. What property do I need? Do I need the stiffness of the clay? Do I need the compressibility? Do I need the strength? What do I need? And then once I know what I need for my design, I can go to the new Eurocode 7 Part 2 and find which tests might be appropriate to get that property. The current code just tells you what the tests are. So if you don't know which test to look for in the first place, you've got a problem. So we hope that the new presentation will be more practical. So we are, for retaining structures, we're particularly interested in the material properties in front of the wall, behind the wall, and also particularly interested in groundwater levels and pressures. So we need to make sure that we have sufficient piezometers in the ground in order to measure those water pressures, or we've got information from wells and other sources, because that is a crucial part of retaining wall design. Now, this diagram is very complicated. It's it's basically a chart showing you all of the geotechnical and investigation standards all on one slide. They're grouped into different categories. So at the top, we've got a suite of standards dealing with laboratory testing of soil. That's EN ISO 17892 is the designation. And you can see around that blue box, you can see there are 12 different parts, all dealing with a different ground property: water content, bulk density, particle density, right through to strength, in shear tests, in triaxial tests, permeability tests, liquid and plastic limits. So depending on which property you need to get, there's a particular laboratory test to get it. So that's the laboratory testing. If you turn anti-clockwise to the left, you see EN ISO 22282 geohydraulic testing. So this is getting water pressures in rock and in soil, water permeability tests using open systems, pumping tests, closed systems. So a variety of standards there dealing with measurement of water pressures in the ground. The next one round anti-clockwise is sampling and groundwater measurements. And this is a very important document. And part 1 is a very large document. It's 350 pages long. It deals with all the technical principles for sampling the ground, getting samples out of the ground, whether it's by coring, percussion drilling. A variety of different techniques are described. The pros and cons of the different techniques are described. The samplers are described. The quality of the sample that you get back is classified. So all of that information is given in EN ISO 22475, sampling and groundwater measurements, part 1. Parts 2 and 3 are not full standards. They're what are called technical specifications. They are dealing with qualifications for the enterprise, the organization, the contractor who is doing the work, and the personnel, and assessment of the contractor and the personnel. And this is the quality assurance side of ground investigation. This is making sure that the people doing the work are sufficiently qualified and experienced, and that's covered by these 2 technical specifications. The reason they're not full-blown standards is that this sort of thing is often different from country to country. So some countries do it one way, some countries do it another way. So it's impossible to get agreement on a single way of doing it all countries adopt. So that's why they're technical specifications. That means countries can choose whether to adopt these or not. The next one round is 17826 geothermal testing. Determination of thermal conductivity of soil and rock using a borehole heat exchanger. And heat exchangers are becoming more important, trying to become more environmentally friendly. So we're using the ground as a source and sink for heat, and that standard helps you with testing to find those geothermal properties. Then the bottom spider is 22476 field testing. This is a very big and important suite of standards, probably the most useful of the lot in this suite, certainly from my point of view. It deals with all the different types of field tests that you can do. So we've got electrical cone and pizza cone, dynamic probing, standard penetration test, Maynard pressure meter test, flexible dilatometer, self-boring pressure meter tests, which is used in the UK a lot, borehole jack tests, full displacement pressure meter tests, field vane tests, something called the weight sounding tests, which I had never heard of, but apparently is used in Sweden quite a lot, flat dilatometer test, the old type mechanical cone penetration test, and then other measuring methods during drilling. So all of these describe the test, how it's conducted, what measurements you take, and in some cases tell you how to convert those measurements into geotechnical properties such as strength and stiffness. So that's, again, all very valuable. Again, going anti-clockwise and now on the right, 18674, geotechnical monitoring by field instrumentation. So this is all about installing inclinometers, piezometers, extensometers, pressure cells into the ground, into the structure, in order to get measurements of ground properties directly, if you like. And then the next one round, identification and classification. There's one EN ISO 14688, which is all about identification and classification of soil, which is where soil descriptions are defined. And then 14689, which is the same but for rock. And when a ground investigation company takes samples and describes the materials that they find, these are the two standards or three standards that they need to follow in their descriptions. And there are some important changes from traditional practice. So when I started, the descriptions were quite different from what they are today. I think younger engineers will have no problems with the new descriptions, but if you're of my generation, there's a little bit of a sea change in the way that soils are described. Soils and rocks are described. Why that is important to be aware of is that you will quite often from your desk study be dealing with historical documents where the ground may have been described using different standards. And you have to be careful when you're mixing old and new documents that you are aware that some of the descriptions may have changed. So that's why it's important to be aware of what the current standard is and what older standards are, because we do rely on those historical ground investigation reports. So that's the suite. You can see there's, I don't know how many there are here. There's over 40 different documents that you may have to look at one time or another. Now, that's just the ground. We've obviously also got to cover the steel. And for that, fortunately, we can often refer to Eurocode 3, particularly Eurocode 3 Part 5, which deals with steel piling. That's the document shown top left. That gives a lot of the design parameters for structural steel, including sheet piling, but the actual material properties come from separate product standards, such as EN 10025, 10083, 10149. They're all dealing with different types of hot rolled products. For retaining walls, we're particularly interested in hot roll sheet piling, and that has its own material product standard, 10248. We also might be interested in cold form sheet piling, so that is 10249. Now, these are very dry documents, they're technical documents, but there are important things in terms of yield stress and strains, toughness and things like that, which may be important in your design, particularly the structural aspects. So that's for steel. For concrete, we refer mainly to Eurocode 2, Part 1. And again, there's a separate product standard, EN 206, which defines the material properties of concrete, including concrete that is used in board piles and diaphragm walls. The original version of EN 206 did not do a good job of describing concrete used in the ground, and there were a lot of complaints about it. But that has now been rectified, and the people writing this standard have listened to ground technologists who have explained that the concrete that we use in the ground has to be different from superstructure concrete because we've got to get it into the ground. And there's the issue of the flow, which is the issue of the durability of the ground. There's a whole different set of technical requirements. EN 206 now covers that, so I'm quite pleased about that. We've also got standards dealing with steel reinforcement. The key thing on this slide is the exposure classes. Obviously, when we're dealing with the ground and concrete, there's the danger of chemicals in the ground and groundwater affecting the durability of the concrete. And the way that we assess that is by what are called exposure classes, what chemicals are likely to attack the concrete. And again, this is all covered in EN 206. The current Eurocode 7 doesn't really deal with this issue at all. The second generation will address it. So it will deal with the structural design of board piles, diaphragm walls, etc. So there's a lot more joined up thinking in the second generation between the geotechnical and the structural. And that's quite important because there is a group of people who do structural design of foundations, and they're often orphaned by the codes because it's not in one and it's not in the other. We're hoping that the second generation will bridge that gap. Okay, so those are the materials. Groundwater is a big issue in retaining wall design because water in the ground effectively halves its strength. If you think about it, when you've got total stress, no water, if you introduce the water, the effective stress is around half the total stress. You've reduced the shear resistance by half. So knowing what water you've got is very, very important. And we need to think about drainage systems, which can be used to control the water. We also need to think about how we introduce reliability into our water pressure calculations. How can we treat water pressures? And how do we avoid going overboard in our safety requirements? So let's first of all talk about drainage systems, and I'm going to concentrate here on the gravity wall type wall, where there's a variety of techniques that we can use. You've already seen the top left one in some of the photographs, weep holes going through the wall, just relieving the water pressure. That's fine as long as the weep holes don't clog up over time. So there's a maintenance requirement here. You can also have drain pipes doing a similar thing, perforated drain pipes at the heel of the wall. That's a possibility. You can have chimney drains with weep holes. If the water is a bit higher on the wall, that could be useful. You can have chimney drains with drain pipes. You can have inclined drains, which pulls the water down further back into the ground, or interceptor drains with drain pipes. There's a variety of things that you can do to take the water pressure off the back of a gravity wall, which is generally a good thing to do. Now, let's say that we can't drain the water away and we're having to deal with water pressures. One question that comes up a lot is whether we should factor water pressures. And it very much depends on your training and often whether you're a structural or a geotechnical engineer. Most of my geotechnical colleagues, and certainly of my generation, instinctively say you should not factor water pressures because they have difficulty conceiving, they imagine that if you factor the water pressure, that you've raised the water level above the surface of the ground. Well, of course, that isn't true. All you've done is introduced a margin on the water pressure. And of course, it's something that structural engineers are quite comfortable doing with the weight of their concrete beams. You have a concrete beam, it's a permanent action, you multiply it by a partial factor of 1.35. You're not imagining that the concrete is 35% thicker. So there's this conceptual problem that a lot of older geotechnical engineers have problems factoring water pressures, and they will often tell you don't do it, whereas in fact, you should do it in the right circumstances. So this is one area where I would defer to a lot of my structural colleagues saying, actually, you're probably right. And I'll come on to how you do it in a moment. So for ULS, the Eurocode requires you to work out your design water pressures as the most unfavorable values that could occur at any time during the design lifetime of the structure. So that could be 50 years, for example. For serviceability, you want the most unfavorable water values that could occur under normal circumstances. And the question here is, what do we mean by normal? If the water is fluctuating because you're next to a river, what is the normal water level? It's meaningless. You really need to talk about probabilities of occurrence and return periods for fluctuating water levels. And that's something that the new Eurocode will do, whereas the current Eurocode is unfortunately very silent about. Now, there is this important clause at the bottom in Eurocode 7. Design values of groundwater pressures may be derived either by applying partial factors or by applying a safety margin. So the question is, which one is it? Which one should we do? So here's a little exercise that was done when Eurocode 7 came out in 2004 amongst geotechnical engineers across Europe. It wasn't done by me, it was done by a colleague. People were asked, given the water pressure diagram shown in B, which is the characteristic water level, the highest normal water level that you expect to occur on the back of the wall, how would you work out your design water pressures for ULS? Now, Eurocode 7 says that you have to consider the highest possible water level during the design service life. So that is C. Unfactored water pressures is C. And then a lot of structural engineers, when asked, will say, actually, I would then factor that water pressure by 1.35 because it's a permanent action. That is D. Others say, well, hold on a second, the water pressure is fluctuating. Therefore, it's a variable action. Therefore, I'll do F, where I factor by 1.5 instead of 1.35. And others are more sophisticated and say, well, actually, part is permanent and part is variable. I'll factor according to E. Now, the trouble with E is it's probably more complicated than it's worth. The trouble with F is it's very pessimistic. The problem with C is it's instinctively what a lot of geotechnical engineers think is correct. And D may or may not be too conservative. When I do surveys on training courses of people, I get a pretty even spread between C, D, and F. And I get some choosing E. Now, what that is telling me is that the code is ambiguous, because all of those designers would end up with different designs because they've chosen different water pressures. And if it's a small wall, it's a very significant difference on your bending moment, not for this gravity wall, but if you had a concrete wall, it would be a very significant difference. So the code needs to do this better. And in our book, Andrew Harris and I recommended the following. If you, in Eurocode 7, there are two calculations that you're going to do on your retaining wall earth pressures. In one of them, you are not going to factor effective earth pressures. That is case 2. And in case 2, if you don't factor your earth pressures, then you shouldn't factor your water pressures either. Otherwise, you're going to mess up Terzaghi's principle of effective stress. But because you're not factoring your water pressures, you should increase the level, the water level, to add a certain amount of safety into the calculation. So that on the bottom right, design water condition 2, I'm not factoring my water pressures, but I've raised the level to the highest possible that I can conceive during the design surface life. But there is a second calculation where partial factors are applied to earth pressures. That's condition 1. And if you're going to apply factors to earth pressures, again, to conserve Terzaghi's principle of effective stress, you should apply the same factor to your water pressure. So you treat it as a total pressure, in effect. That factor is normally 1.35. So in the diagram, in the middle, if you're factoring by 1.35, that is probably sufficient to cater for the uncertainty in the water conditions. So apply that without raising the water level. Now, this is an interpretation of the current code, but I have found in the last 10, 15 years that this holds up in a lot of circumstances. Very rarely will this combination, checking both, not cover the uncertainties. So this is a practical way of interpreting the code. It's not what's written in the code, I'm afraid. The code is ambiguous, but if you follow this, you won't go wrong. The second generation of Eurocodes, I'm pleased to say, will make this unambiguous and will effectively adopt something which is equivalent to what I'm showing here. So this is what I would recommend that you do, but you won't find it in the code, I'm afraid. Okay, those are some fundamentals. Now let's talk about geotechnical analysis. And I'm going to go through calculation models in the next lecture in detail. But before we get there, I need to talk about some of the parameters that we put in, because it's important that we put the right parameter into the calculation models. So the first parameter that we need to think about is the angle of interface friction between the ground and the wall. And this is being complicated by Eurocode 7 because it tells you that the angle delta design should be calculated using the constant volume angle of shearing resistance, phi CV. Now, geotechnical engineers should know what that is. I suspect that many structural engineers won't know what that is unless they've done a geotechnical course during their training. The constant volume angle of shearing resistance is the angle of shearing that you get when the soil no longer, at large strain, when the soil is no longer expanding or contracting. So it's constant volume. It's also known as the critical state angle of shearing resistance, which is a theory developed at the University of Cambridge in England and has been widely adopted in many other practices. The diagram on the right shows you what is happening. On the vertical axis, I'm plotting the effect, the mobilized angle of shearing resistance, phi. Along the horizontal axis, I'm plotting displacement. So in a shearing test, if I shear a dense soil, which is either a dense sand or an over-consolidated clay, as I shear it, the clay will expand. It'll expand because the particles have to roll over each other, and they, rather than break the particles. So in order for the particles to roll over each other, the soil has to expand, which increases the pressure in it. And you get a peak resistance, which we'll be familiar with. If the ground can continue to shear, then that you get a post-peak behavior, and it'll fall down, and the effective angle of friction at large strain drops from phi peak to phi CV. Now, you don't see that in a regular shear box test or a regular triaxial test because the sample breaks after the peak. You have to do a particular type of test to measure that post-peak behavior. It's a similar problem with testing the strength of steel, which has a peak and then a post-peak behavior. Brittle materials. On the other hand, some soils are loose and contractant. So a loose sand or an under-consolidated or low-consolidated clay. In that case, as you shear it, the soil, which is the dashed line on the diagram, you never see a peak value. It just, the shearing resistance just increases, and at large strain, it eventually reaches the same phi CV value. So this phi CV is quite a fundamental property of soils, and that's why it's part of the critical state value. The extra bit of shearing that you get in a dense soil is called dilation, and there are ways of calculating these two things separately. Now, what Eurocode 7 says is you calculate the wall friction based on that large strain value of phi, and that is sensible because you're getting large, at ultimate limit state, you're getting large shear strains adjacent to the wall. The problem with it is that routine ground investigation doesn't measure that peak value, that critical state value. Consequently, people don't have the value. The other problem is we really don't need to factor that phi CV value because already it's a pessimistic value. You're going to get that value eventually. Why are we factoring it? So the second generation of Eurocodes will provide a separate factor on phi CV so that you're not having to apply a factor of 1.25. This is where the current Eurocode is not giving good advice, and most experts advise you to do something slightly different. National annexes often give you a way of doing that, but this is where I would depart from the standard, the current standard. Now, I said that you can get this constant volume value in a number of ways. Here are some formulations. These are taken from the British standard for retaining walls, which I was involved in writing. For sands and silts, we have a formula. Phi CV is 30 degrees plus a value due to the angularity of the sand and a value due to its particle size distribution. If the fines content is less than 15%, you add on a value due to dilation. And there's a formula that you can use to get that dilation based on density index. So if you want to get a value from this sort of formula, you can get it from other material properties in your ground investigation report. If you've got a fine soil, there are a number of correlations. This is just one at the bottom, showing how you can get FICV from plasticity index. And then the dilation is maybe give you up to 4 degrees on top of it. So if you haven't got much information, these are rules of thumb that you can use to get additional information. And here are the tables giving you the values of the phi angular, phi PSD, phi dilation for different conditions. I won't go through that. You've got that in your notes. And this is the justification for the constant volume of angular friction for clays. It actually dates back way back to Terzaghi and Peck. They had similar information. This is more modern data. But there's lots of testing to show that these sort of values apply. So again, here's some rules of thumb to get you practical values that you may not have from your ground investigation report. Obviously, if you can specify the tests to measure the parameter, you should always do that. But if you're given a ground investigation and you haven't got the data, this is a way to fill in the gaps. Okay, so that has covered the some of the parameters that we're going to see later. Let's talk about execution. So execution is the method of us constructing the walls. And I talked about the European standards for geotechnical investigation. There is another set of standards, European standards. These are not ISO, these are just European, dealing with execution of geotechnical works. They're for embedded walls, for diaphragm walls, for sheet pile walls. And in the UK, we have a book published by our Institution of Civil Engineers dealing with all of these, and that is called Spur Wall. And it's a very useful document, something I think that would be useful to you even in Latvia. It's not particularly UK-centric, but it's a very valuable book. So let's look at these execution standards. There's a range of them. I think there's 13 or 14 of these now. They cover walls and steep slopes in brown. They cover pile foundations in green, which we're not covering today. They cover ground improvement techniques. So for retaining structures, diaphragm walls, EN 1536, sheet pile walls, 12069, anchors that we need for the walls, 1537, soil nailing and reinforced soil, I've already covered those. Jet grouting we might need if we're doing a jet grouted wall. Board piles we might need, not just for bearing, but also for lateral resistance, micropiles and displacement piles. So actually, most of these standards could be relevant for retaining wall design. This is what they look like. The one on the left is the British cover. The one on the right is, again, the British cover, but these are what the standards are called and look like. And what I've done in your notes is give you mind maps showing you the sort of content. It's not worth going through the detail of the content. It's all specification material. It's all about what are the properties of the supporting fluids, the slurries, the concrete, the mortar, and the steel. What should you specify on your job? It covers stability of a panel excavation. This is the one for diaphragm walls. It covers the design of the reinforced cage. It covers things like the concrete cover. What do you need to apply? All this detail is not in the Eurocodes. It's not in Eurocode 2. It's not in Eurocode 7. It is in these execution standards. So if you're a designer, you need to be looking at this because it will give you the practical details that the contractor is going to need to know and work to. And if you're doing a design, you need to be aware of these details. So that's the one for diaphragm walls. We've got another one for sheet pile walls. So here we're talking about steel piles, timber piles, other types of pile. We're talking about corrosion protection, sealing for interlocks. On the right-hand side, welding is important for sheet pile walls to prevent out-of-plane bending. Driving of sheet piles is very important, makes a big difference to the performance. Tolerances on plan position, out of tolerance, wailings and struts, all these sort of things are covered here. Again, design details, not design principles here. Now, I say that I'm not going to show you all the other ones, but that gives you a flavor of what is in these particular standards. I mentioned this spur wall document. This is what the book looks like. It's been around for a long time. It was first published in 1996. It's now in 2016 edition. It gives you a nice summary of those execution standards, particularly for piling and embedded retaining walls. As far as I'm aware, it is written by people from British industry. That is true, but the recommendations in there should be fairly universal. Because they're based on the European execution standards. So I think this is a book that has value outside of the UK. So that's why I recommend it to you. Now let's talk about some other guidance documents that you might want to look to. Obviously got Eurocode 7. We've got the basis of retaining wall design. We've got a British standard that I want to talk about. We've got a Syria document. We've got a German EAU recommendations. And these are documents that you can turn to for design details. This is the sort of information that I can't cover in today's course. If I was to cover all this material, it would be a 3-day course. But here are the documents that you need to look at. Obviously, Eurocode 7 Part 1. And as I said, Section 9 deals specifically with retaining structures, but so does 1 or 2 of the annexes, which I'll cover later. Also, Section 8 dealing with anchors. Also, Section 5 dealing with fill, dewatering, ground improvement and reinforcement. There's a little bit of the material there. I've also mentioned that in the second generation, there will be further information. For this, the rules about retaining structures move from Part 1 all the way down. My slide, unfortunately, is again off target. That information moves into Eurocode 7 Part 3, geotechnical structures. There's a clause on retaining structures, there's a clause on anchors, there's a clause on reinforced fill structures, there's a clause on ground improvement. So there are separate clauses on each of those topics and annexes to go with them. Now, I mentioned the British standard, and again, the reason for recommending this, I was involved in it, so I know its content, but again, a lot of the information in here is usable outside of the UK. It is a document that is fully compatible with Eurocode 7. That's what makes it usable outside of the UK. And it's fairly up to date. It was published in 2015. Now, a lot of the material that is in here, I'm going to cover in the next set of slides, the next lecture. So, but I point you to that document in case you want to follow up. Also in the UK, we have a document called Syria C760, which is very widely used. And again, this could be used universally. It's of a standard that makes it an internationally valuable document. It's a follow-up to previous documents that date all the way back to 1984. It was prepared following extensive public consultation with the industry and is fully compatible with the British standard, which I've shown you here, and the Eurocode. So these 3 documents all work together seamlessly. Eurocode sets all the principles out. The British standard fills in a lot of details specifically for retaining structures, and this document gives you more detailed guidance on embedded retaining wall design. It's only for embedded retaining walls. It discusses wall types and construction methods. It has a very valuable database of ground movements for different types of retaining walls. So somebody asked the question, how do we work out ground movements? Well, quite often we do it by looking at case histories. And this summarizes the international database of case histories for movement of retaining structures. And again, that is universally applicable. It is very up to date with modern techniques. So again, I would recommend this document to you. And another document I would strongly recommend is the German document, commonly known as the EAU, which is the recommendation of the Committee for Waterfront Structures, Harbours and Waterways. The German edition is on its 11th version. there's an English translation, which is the 9th edition. And the fact that we're on a 9th English translation tells you how valuable this document is. It's produced by the Port Technology Association, the German Geotechnical Society. It's got a lot of very, very useful information in it. And if I'm doing a retaining wall design, I'm using this equally with the Syria guide from the UK and the British Standard. I regard all of these documents as very valuable, no matter which country you're working in. So that covers the guidance documents. So what I've tried to say in this lecture is you've got a large variety of materials and techniques, and there are many, many standards that you need to look at, particularly in ground investigation and testing. Further standards for material specification for steel and concrete and all the other materials, and then a further suite of standards for execution. So if you are doing design, you've got a lot of documents to refer to, unfortunately. But if you want to do the right job, you do need to look at those documents. There are supporting documents that bring many of these things together. They're not a replacement for, but they're supplementary to the Syria and the EAU documents in particular. Okay, that brings us to end of part 1. We've got time for some questions. Petrus, what have we got?
Yeah, we are having more and more questions, which is good. Probably for now, I will go with 3 questions, and the rest we can leave for
later.
For okay. End of today's lecture. Okay.
Yes.
So there were 2 questions regarding water pressures. One was actually answered, but maybe to make it clear, how far we can use these recommendations you presented. I mean, how far we can. Yeah, and like following the current code, exactly about the partial factors. You presented this yes, recommended approach you presented. How is it okay to use it?
I would not use the partial factors from the 2nd generation of Eurocodes yet until your national standards body says so. So the 2nd generation codes only come into effect in a particular country when the national standards body say so. So it will be down to your Latvian national standards body, and it may be different in your country than in the UK, for example. So I would very much stick to the existing Eurocode because those are published documents. The problem, as I've mentioned, is that the existing Eurocodes are ambiguous in places, and we've learned over the last 10-15 years that there are problems that we need to solve for practical design. So from that point of view, looking at the new code and looking at things like the guidance documents that I've mentioned is a good way of solving problems that the standards don't solve. Obviously, you are responsible for that, for choosing the right guidance. The standard is not pointing you necessarily to those documents, but that is what you will have to do if you want to get practical designs out. So that's the purpose of courses like this. I can recommend to you where you've got good sources of information, good advice. Obviously, I'm not mentioning where not to go, but these are the ones that I would have no hesitation in recommending to you. But I would hold on using the partial factors from the new Eurocode until they've been endorsed by your national standards.
Okay. And then there was another question, more practical, about water pressures in the design. Well, there was an example when you have second pile wall, and very often, at least in Latvia, there is wall in front, like reinforced concrete wall in front of second pile wall. And the question was, should we apply water pressures on that wall in front? Meaning, should we assume that the second pile wall can lead the water through, or yeah, this is maybe a more practical question. Maybe you have some ideas.
Normally, the facing wall is not a structural wall. It is not normally designed as a structural wall. So from that point of view, you are assuming that the water pressures do not transfer through into that wall. It is merely a facing. If the water has the possibility of transferring through and building up pressure, then you've got two options. You either got to design that facing wall structurally, in which it's a structural wall, it's got to take the pressure, or you've got to put a drainage system in to catch the water. You must be careful not to have a non-structural facing wall where you could get the water pressures building up behind, because obviously that will fail. So it does very much, it's very project specific. But if water water will get where water wants to go. It's very difficult to stop it getting to places that you don't want it to get to. So if you've got water pressures, you need to take positive action to control them, which is either through a positive drainage system, or it's by having sufficient structural strength to resist the pressures. And really that's what you can do.
Okay, and maybe the last question about these execution standards you mentioned, because some cases we go to the nonsenses in on the construction site when, for example, inspector or even designer is like sticking to these points, and the question is how much. These execution standards sticking to some specific points, and the question is how much they are as a rule or how much they are recommendations. Because I believe, well, that there is something which is rule and which is recommendations, but maybe in general, could you explain about these execution standards, how much they are as a rule?
They are full European standards. They have shalls in them. You have to follow them. And the Eurocodes make it very clear that the designs are based on the assumption that you will obey the execution standards. Now, don't worry about that, because from a practical point of view, because I know the worry is, oh, we've got impractical design rules and we can't follow them. The execution standards were actually written by engineers from contracting organizations. So many of the people who are involved in the writing of those standards, rather unusually, did not come from academia. They did not come from consulting practices. They came from contracting companies. So they are very practical documents. And they are what I would call light touch standards. They only ask for things which are necessary and achievable. The execution standards have generally got a very good reputation because they're what good contractors do follow, because it's in their interests to follow. So I would have no hesitation following an execution standard. They can always be improved, of course, but there's far less wrong with them, if you like, than gaps in the current Eurocode 7. The Eurocode 7, the current version, there's lots of compromises between countries. The execution standards were pretty well universally and unanimously agreed. But they are full European standards. If you're building a retaining wall, you have to follow them. And that will probably be in the contract that you sign for the work.
Okay, the rest of the questions I think we can keep for the end of the lecture.
Okay, excellent. Thank you very much for that. So let me move on to the second part of this lecture. Bear with me a second. Again, you've got a list of references there. So again, same topics, but I'm moving to the second half of the list here. And let me click on that link. Okay. So here, I'm now going to go through, going back to theory, and we're going to look at earth pressures. We're going to look at these aspects of design. I'm going to look at what's important, what isn't important, and some of the methods of analysis that we use. And a lot of the material in this particular lecture comes from the Earth Pressure and Earth Retaining Structure book. So, earth pressure theory, back to fundamentals. There are a very large number of things that affect the earth pressure behind a retaining wall. The surcharge on the ground surface, the inclination of the ground surface, the inclination of the wall, Water tables, we've been talking about, not just water tables where the water is static, but seepage water tables, water flowing round a wall. Swelling of the ground, strain ratcheting, where the wall moves, stops, often involved with the presence of ice. The amount and direction of the movement of the wall relative to the ground. Is it active conditions or passive conditions? Vertical equilibrium of the wall is important. And then we're into the shear strength and weight density of the ground. The ground is a major contributor to the forces on the wall. So we've got forces coming from the structure, but the ground contributes a large proportion of the permanent action on the wall. Inclination of those ground strata, initial stresses in the ground. Have we got an over-consolidated clay or a normally consolidated clay? The horizontal stresses can be very different in those materials. And then the rigidity of the structure itself and any supporting system. So, and wall roughness. So there's a vast number of elements and properties that come into the design. So the first thing that we look at with earth pressures is whether that is the condition, whether in at what it calls a limiting state, active or passive earth pressures. And there are a number of ways of getting these values, which are the values that you will use in ultimate limit state calculation. So when you're doing your ultimate limit state calculation, you're going to be pushing the wall to failure so that you can show that it doesn't occur. And that means you will quite often approach an active or a passive limit state. And I'm going to cover all of the topics shown here. So for soil that is in an active state, we have a formula which is how it'll appear in the second generation of Eurocodes, but you'll find it in any standard textbook. It's nothing unique to the Eurocode, which says that the total pressure on the wall at a particular depth is equal to the effective pressure plus the water pressure at the same depth. Now, in many cases, design practice requires us to apply a minimum total pressure to the wall, and that is purely to make sure that we've got a sufficiently safe design. It's like a safety margin, but it's common practice to assume a minimum earth pressure on the wall. The idea being that if a gap appears between the wall and the ground, it will fill up with water or earth or whatever, so there'll always be a contact pressure. So that's on the active side. On the passive side, the wall is pushing into the soil, and the passive earth pressure, the total passive earth pressure is the effective plus the water pressure. And the difference here is that we don't normally apply a limit to this, certainly not a minimum. We might apply a maximum depending on how large we estimate our passive pressure to be. Normally, we restrict the passive pressure by the application of partial factors. That's what they're there to do, to limit the amount of passive pressure that we mobilize. So in the new Eurocode, you're going to see this formula, which is how you calculate the active and passive earth pressure. You have three earth pressure coefficients, K gamma, Kc, and Kq. K gamma, you have an active version, Ka gamma, and a passive version, Kp gamma. And that is the earth pressure coefficient that you multiply the weight, the vertical stress in the ground, which is the weight density of the ground accumulated down to the depth, less the pore pressure. So that's the effective vertical stress times an earth pressure coefficient, which turns it into a horizontal stress. We then take away or add on any benefit or disadvantage due to effective cohesion in the soil using the earth pressure coefficient Kc. And we then add on the effect of surcharge on the wall, which we multiply by Kq. Now, on the excavated side of the wall, we tend to ignore the surcharge because it may or may not be there. So that last term usually only occurs on the active side of the wall. Now, K gamma and Kq for vertical walls are equal. So you often call that K, Ka or Kp. But from a theoretical point of view, if you've got an inclined wall, which you would for a gravity wall, they are numerically different. And I'll cover that in the next few slides. So this is the fundamental equation giving us earth pressures on both sides of a retaining wall. So that's in terms of effective stresses. But for undrained conditions, we can simplify things. And this is for clays and silts. If we have undrained conditions, we can simplify things by using a total stress analysis using the undrained strength of the fine soil. So this is a subset of the previous equation with the pore pressures removed and everything done in terms of total stresses. In this case, K gamma and KQ are equal to 1, so they disappear from the equation. Now, how do we get these earth pressure coefficients? Well, there's a large number of theories. These are the most famous ones. Coulomb, 1776, Maniel, Rankine, Muller-Breslau, Kakko and Carousel, Carousel and Apsey, Brinch-Hansen. That should be 1970s for Brinch-Hansen. Sorry, I'm missing the date there. Each of the theories that have been developed take into account some, but not all, of the parameters that I listed on the first slide. So alpha is the angle of inclination of the wall. So most of them dealing with vertical walls, but Muller-Breslau is dealing with inclined walls, and Brinch-Hansen is dealing with inclined walls. Most of them have a sloping ground surface beta, but Coulomb and Bell don't. Some of them deal with effective cohesion, Bell, Packshaw, Carousel and Apsey, and Brinch-Hansen. They all deal with the angle of internal friction of the soil. That's a fundamental parameter. Some of them can deal with adhesion between the soil and the wall, CW. And most of them, they all deal with wall friction, but some of them assume zero wall friction. Some of them, like Rankine, are limited to wall friction that equals the angle of inclination of the retained surface. So you can see every theory has a set of limitations, and so they're not all good for all situations. And at the bottom of the slide, I've indicated which of these theories are used in standards. So the British standard CP2, which is 1951, was based on Packshaw. In 8002, 1994, it moved to Carousel and Apsey, and in the latest, it also deals with Brinch-Hansen. So the ones nearer the bottom have tended to be adopted in modern design standards. So let's look at the way that these mechanisms differ. And here I brought together 3 different types: Coulomb, Maniel, and Muller-Breslau. These all assume wedge-shaped mechanisms, which means that the results that you get are upper bounds to the value because they're assuming a mechanism. You can see the forces. They basically assume a wedge shape. They do some calculations on the forces, and they end up with an earth pressure coefficient, which allows you to get the thrust QA. And the difference between them is the mathematics gets better the later you get on. So Coulomb is a fairly simple problem. Muller-Breslau is a more sophisticated and more developed set of mathematics. And so the Muller-Breslau formula is this. Ka and Kp are given by this formula, taking into account the angle of inclination of the wall, which is alpha, the angle of inclination of the slope, which is beta, the wall friction, which is delta, and the angle of interface friction of the soil, which is phi. If you substitute 90 degrees for alpha, 0 for beta, and what else have we got? And 0 for delta, you will collapse and get back to the Coulomb equation. The 1 minus sine phi over 1 plus sine phi. But for practical design, you basically want to be able to calculate this. So you can either put that into a spreadsheet, or you can use software which has already got this pre-programmed, and that will give you the Ka and the Kp. So that's one very widely used formula. The other formula that is often used is the Rankine equation. And sometimes this is used when it shouldn't be used, and it's used badly. Rankine looked at the states of stress in the ground and drew more circles of stress and then managed to calculate the earth pressure coefficient, the thrust QA on the little inset diagram to the top, and that ended up being the thrust on the wall. The problem with this is that it assumes that the wall friction is the same as the angle of inclination of the slope, which is in practice very rarely the case. So if you've got sloping ground, you're going to have wall friction of some sort. If your ground surface is horizontal, you're losing the benefit of the wall friction. So it's not a good method compared with more modern methods. It also can be very unsafe when you're calculating passive earth pressures. So a warning not to use it for passive earth pressures. And similarly with Coulomb, I think you've got to be careful using for passive earth pressures. So this is Rankin's formulation. It's simpler than Muller-Breslau's, based on a completely different set of theory. When the inclination of the ground surface is 0, you get the simplified formula on the right, which is the Rankine formula that most books will quote to you, but the correct formula is the one I'm showing here. Notice that in this formulation, when the ground surface is horizontal, Kp is equal to the inverse of Ka. So that's a simplification when the ground surface is horizontal. But this isn't the method I would necessarily use nowadays. You're more likely to be using nowadays something based on a more realistic failure mechanism. So the Coulomb-Muller-Breslau were using triangular wedges, but more modern thinking has said, well, actually, what we observe is a log spiral mechanism. So if you look at the shape of the failure mechanism, bottom right, this is it's not circular, it's log spiral about an origin shown to the left there. This has been found from experiments to closely mimic the actual failure surface that occurs in practice. The mathematics for this is quite complicated to an extent that Carousel and Absi Cacco and Carousel did it first, and it was updated by Carousel and Absi. This is a French scientist's development. They produced a book of numbers. So there's a red book, which I've got on my shelf somewhere, which has got all the earth pressure coefficients in it. And these are two charts plotting those results. These charts appear in Eurocode 7. They appear in the existing Eurocode 7, which will give you the value of Ka on the left and Kp on the right. Be warned, these are logarithmic graphs. So be very careful. The spread on the right is a lot greater than the spread on the left, although it doesn't look it from the chart. Because of the logarithms, that's hidden. The other thing to note is that each chart is for a specific delta upon phi. On the left, well, on both of these are 0.66, 2/3. Now, that's delta upon phi. You've got to work out the correct delta and the correct phi to use there. We've talked about that in the previous lecture. And then the lines are for different angles of inclination of the slope. So you can very easily use this to get a Ka and a Kp. Other developments in Denmark, Brinch Hansen and subsequently a guy called Lundgren have developed what is called the method of characteristics. So the Cacco and Carousel mechanism, this is again an upper bound. This is a log spiral mechanism, whereas the Brinch Hansen and Lundgren is a lower bound. It's a method of characteristics. It's looking at the stress state in the ground. So it's like Rankine's method, but it's more sophisticated. And you have various stress characteristics, and the mathematics is done on either the wedge next to the wall, the wedge next to the ground surface, or the fan mechanism in between them. And there's a lot of mathematics behind it, which I have to say I don't quite fully understand, but you end up with a formula. And this formula deals with angle of interface friction between the wall and the soil, inclination of the ground surface, inclination of the wall, and also the angular phi value of the soil. It's more complicated to code up in a spreadsheet. There are some limits to its use which are not stated here or in the Eurocode. If you run the mathematics, you'll find it'll break down on certain values. You need to be aware of that. But this again is something you'll find modern software will implement and provide you values for. Now, in our book, we thought that it would be useful to provide charts based on the Brinch-Hansen formula that you can look up the values very easily without having to do all the horrible mathematics. So here are the charts, and we've plotted these charts on a linear scale, not a logarithmic scale, because in practice, you need to know that on the right, the spread of passive values is much greater than the spread of active values on the left. Notice the scale change as well. It also indicates that you can make an error in your estimate of Ka, and it won't make much difference. If you make an error in your estimate of Kp because you've got the wrong phi, you've got the wrong delta, it can make a very significant difference. So that makes you focus on the parameters that you use on the passive side in particular. That's an important thing to note. So that's why we've plotted this in terms of linear values. Now, I've been talking about active and passive conditions, and of course, they may or may not apply depending on how much movement of the wall occurs. And this is a diagram showing you the development of earth pressure coefficient K on the vertical axis against relative wall movement normalized by the wall height. So this is the wall movement horizontally divided by the wall height expressed as a percent. If the wall moves away from the soil, you're in active conditions and the earth pressure coefficient drops. The earth pressure on the back of the wall drops as the wall moves away, and you drop to that bottom level, 0.2, 0.3 shown here, at about 1%, 2% deflection ratio. You don't need very much movement of the wall away from the soil to reach active conditions. But look at the right-hand side. To get up to the very high passive earth pressure coefficients of 3 and maybe even 4, you need a lot more movement. You need 3% movement in order to get up there. So you need much greater movement. Not only that, the amount of movement that you need depends on the initial stresses in the ground. So if you've got a K0 of 0.5, which means you've got a normally consolidated soil, so maybe a soft soil or a not particularly highly compacted sand, you're on the dashed curve, which means that you've got to move quite a bit further to get to passive than you have to get to active. You need very little movement to get to active. If you look, you're starting at 0.5 where it crosses the axis. You need 0.5% movement to get to active, but you're going to need 3.5% movement or 3% movement to get to passive. If your soil is over consolidated, so it's been it's a very dense sand, it's had lots of overburden on it in the past geologically, which you'll only know from your ground investigation, your K0 might be 2.5, for example, in which case you're already starting at the axis high up. You now don't need so much movement to get to passive. You need more movement to get to active. Now, what we've got to do is we mustn't underestimate the active pressure and we mustn't overestimate the passive pressure. Those are the key conditions in the design. So understanding wall movement relative to the in situ stress state is very important. The other thing you should note here, of course, is if we introduce props into a wall system, that prevents the movement. So if you prop a wall as you excavate beneath the props, you may not be able to, the wall may not be able to move away from the soil. You may not drop from K0 to active. So a lot of walls where we prop them, we may not take Ka pressures, we may take K0 pressures instead, because the propping keeps the pressure at a higher level. So you have to bring that into mind as well. The other thing to note is as we excavate in front of a retaining wall, we are almost certainly forcing the soil to go into a passive mode of failure. even without any movement of the wall, because we're just excavating the soil, we're relieving the overburden, we're going to end up at passive failure. So there are certain conditions you can predict quite easily just by the activities that you're undertaking. Okay, so I've mentioned at-rest earth pressures. Let's take a look at those. These are much more difficult to predict. There isn't a reliable theory that gives it you perfectly. There are a number of formulae in the literature. The most famous is probably Jakey's 1944 solution for normally consolidated soils, which is given there. You will often see the second term in brackets omitted from most textbooks, wrongly omitted. This is actually what Jakey published, but most textbooks give you 1 minus sine phi as Jakey's formula, but it's actually slightly more complicated. In 1963, a guy called Hendren came up with a more sophisticated solution, looking at, I don't know whether they were glass spheres, but little small spheres of material. And this is a theoretical formulation for K0 based on PhD research. And the formula is quite horrible. I've given you a slightly simplified version after the equality slide, just try to simplify that down. It's similar in shape to Jakey's formula, but it's not quite Jakey's formula. Brian Simpson, who was very heavily involved in the Eurocodes during his career, he developed what is called the brick model, and this took it into account stress history and the rotation of stresses, and he came out with a formula for K0, 1 minus 0.7 sine phi over 1 plus 0.7 sine phi is an approximation. Similar to Hendren's formula, not too dissimilar to Jakey, but again, based on a different set of theory. And finally, quite recently, Federico and Ilya have come up with another correlation, which is pretty similar to Simpson's. Now, when we compare those equations, you end up with a fairly useful chart to be able to work out what your K0 might be based on your angle of internal friction. So if you need to know what your K0 is, here we have a way of doing it for normally consolidated soils, or something that is close to normally consolidated. You can see the spread of results. The dashed line is in fact the active earth pressure limit. So the green line going below that is a rather strange and rather questionable. So personally, if I was using this, I would be using the top 3 lines, Jakey, Simpson, and Federico and Elia. They seem to be fairly consistent with each other. Given the uncertainty we have in phi, that's a reasonable approximation. So there's a practical way of getting at-rest values of K0 for normally consolidated soils. Now, of course, a lot of soils are not normally consolidated, so you need to get over consolidated values. And the most commonly used formula for that is due to Meyerhof, and this formula appears in the current version of Eurocode 7. 1 minus sine phi, the Jakey simplified version, times the square root of OCR, over consolidation ratio. The over consolidation ratio is your estimate of the horizontal stress to the vertical. No, that is wrong. My slide is wrong there. It is not sigma H over sigma V. It's the pre-consolidation pressure. That should be sigma dash P divided by sigma V. I apologize, there's an error in that slide. There have been more modern attempts at looking at this. Paul Main in the US has done a lot of work on this and came up with a slightly different version. 1 minus sine phi to the times OCR to the sine phi. And Eurocode 7 combines the Meyerhof formula with an adjustment by a guy called Kesdy, allowing for sloping ground. So if you've got sloping ground, you can also work out what your K0 value needs to be. So there again are some practical rules. These are as good as you're going to get at the moment. We don't really have any better feel for these values than we're giving that we've got here, unless you go and measure the value, and you can obviously do that with instrumentation. Now, so far, I've just been talking about earth pressure due to natural ground. But of course, in many cases, we place the ground and compact it behind a retaining wall, particularly for gravity walls, less so for embedded walls. And compaction earth pressures can be a lot higher than Ka. They can be even higher. Well, they can appear to be higher than Kp. What happens is as you compact each layer, so if you imagine the diagram bottom left, we're putting layers of soil down. And as we do, the soil goes into passive failure. As we compact it, we're forcing it into passive failure. So the upper layers of the compacted ground has an earth pressure coefficient equal to Kp. The earth pressure goes up very steeply. But as we put further and more layers on top, the first layer that we compacted forgets the fact that it's a passive and its pressure starts to drop. And you end up getting a plateau. Sorry, it doesn't start to drop. It no longer increases at the same rate. So what you get is you get a limit value, a plateau in the earth pressure increasing with depth. So in the middle diagram, you've got the simplest version, which is the one that I would use. You've got passive earth pressures down to a depth Zp. You've got a fixed earth pressure down to a depth Ze. And after that, you've got your regular K0 pressure, potentially K active pressure. Now, the formulas in the top right will tell you how to get the numbers at the different depths. The bottom right formulation is something that is used in German practice with a slightly more sophisticated formulation, but I'd have thought the one in the middle is sufficiently good for most practical purposes. So if you're dealing with compaction, then that's the sort of thing that you should be looking at. Okay, so that's the theory that we're using for earth pressure calculations. How do we go about doing the analysis? Well, for this, we've got to use different models: limiting equilibrium, beam on spring, earth pressure envelopes, and distributed prop loads, or continuum numerical models. So the limiting equilibrium methods have been around a long time. They're the most commonly used for simple structures. They are where you consider active pressures on the retained side, passive pressures on the excavated side. If you've got a cantilever wall shown at the top, you are assuming a point of fixity O at some point and rotation about that point. So the earth pressures cross over at that point. Obviously, these triangles are idealized profiles. In reality, there's no sharp changes in earth pressure, but these are sufficiently good that you can do a lot of design, particularly for cantilever walls, based on this. The bottom diagram shows, and that the top one is called the fixed earth method. The bottom diagram is called the free earth method, where we have rotation about the prop and we have no constraints of the pile of the retaining wall going into the ground. Based on those assumptions, you can then do your stability calculations. What we need to do is make sure that the pile does not, the wall does not rotate about that point O. The question is, where do we put the factor of safety? And there are, here I show 4 traditional methods of doing it. The top left is to apply the factor to the passive earth pressure. So we've reduced the white triangle down to the gray triangle, and we only factor the earth pressure, not the water pressure. On the top right, we have what is called the net pressure method, which takes the difference between the pressure diagrams and then applies the factor to the net passive pressure. This was a very popular method because you can do hand calculations with it very easily. The problem is it gives you artificially high factors of safety for fairly small increases in pile embedment. So it's a method that's fallen out of favor in modern times as calculations are done by computer. Why use a simplified method when you've got better methods? The bottom left is where you apply a factor to the depth of embedment of the wall. This is shown to be very unsafe in some certain circumstances. It gives you a very exaggerated factor of safety. I would strongly not recommend that you use this method. It's very much fallen out of favor. And then on the right, we have the method that is now used by most modern codes of practice, which is where you factor the material properties, your tan phi and your C dashed, and you increase the active earth pressures and simultaneously decrease the passive earth pressures. So, and then do your calculation. So you change the pressures on both sides of the wall and then do the calculation. This has to be done by iteration. There's no other way of doing it. But this is the method effectively that is embedded in the Eurocode and any modern design standard. To do the calculations, you're going to need software. You're either going to have to put it into a spreadsheet. You can do it by hand, but in practice, if you look at this, this is the software that I've written that does this, called Reward. If you look at the earth pressure diagram in the middle bottom, if you've got multiple layers, so we've got a sand and a clay and a sand and a clay, the number of calculations you have to do here to get to an answer is not worth doing by hand. You'd go crazy. It'd take you a day to do it. So software will do it for you. There's a variety of tools available. Limiting equilibrium software can easily be obtained, and that'll save you a lot of time. You can now you can use the software and concentrate on the engineering, not on the calculation. So use software tools to do this. So that's limiting equilibrium methods. There are also programs that will do what are called beam on spring calculations. And these are supposedly better. I say supposedly because the only difference between them and the limiting equilibrium is shown in the top right corner. In a limiting equilibrium calculation, you are assuming perfectly plastic behavior. You're going immediately to failure, and you have passive and active limits. With a beam on spring model, you're assuming linear elastic, perfectly plastic behavior. So you're allowing for some displacement before you reach your limiting condition. The limiting conditions are still active and passive earth pressures using the same equations that I've covered for Ka and Kp. The only difference is we've got to put a value on the stiffness K of the spring. And this is known as subgrade reaction. And unfortunately, it's not a fundamental parameter. It depends on the soil, it depends on the area. It's not something you can get from a laboratory test. It's typically something that is back calculated from previous jobs and is then used as a rule of thumb. In the Winkler model, you have to remember that the K that we're talking about here is not the same as Hooke's spring constant. Hooke's spring constant is force divided by displacement. In the Winkler model, which dates back to 1867, it's pressure divided by displacement, and it's the area involved which is the complication here. Here's a formula that will give you the K based on stiffness, and H being this sort of unknown dimension. And then you can put this into a computer program and work out the bending of the beam using normal structural mechanics. Now, some companies claim that this is a finite element analysis. Well, it isn't. It absolutely isn't finite element. The only bit that's finite element is the beam calculation. The actual ground calculation is Winkler spring. Let me just say what the advantage. So I should have said what the advantage. The advantage of this is you will get a prediction of movement, but it's only as good as your confidence in the spring constants that you put into the calculation. So how do we get another way of getting earth pressures, particularly for multi-prop walls? Well, for this, we commonly used earth pressure envelopes, which date back to Peck's work in the Boston Metro in the 1960s. And he and Terzaghi published a whole series of diagrams shown on the right that allow you to work out an equivalent earth pressure based on what they measured in the props. So they actually measured the prop forces and said, okay, if that's the prop force, the earth pressure must have been this. But these are envelopes. This is an envelope to the biggest pressure we measured. If you use these, you are automatically being cautious. You've automatically got your safety factor built in. There is various sophistications on this, but this has been a very widely used method and it's still in current practice. It has been updated, certainly in the UK, by what is called the distributed prop method. And really, this is just a name change because there was a worry that earth pressure envelopes were being used as earth pressures, but they're envelopes, and people were forgetting that fact. So what the Syria document that reviewed all of this material did was said, no, we're going to call it a distributed prop load. You should only use this to get the prop load. You should not use this to get your bending moments. So slightly different diagrams, a more comprehensive database of soils. You've got to remember that the PEC diagrams are based mainly on Boston blue clay, so a limited range of soils, whereas this is a bigger database of soils and a bit more sophistication in the method. So you've got some classification of the soils, and then you've got some values for the prop load as a multiplier times gamma H, where H is the retained height. So here's a more modern version of the Terzaghi and PEC envelopes. I would certainly recommend you looking at this. It's quite a valuable method. And then finally, we've got continuum models, finite element, finite difference, boundary element, various models that attempt to model everything. And obviously, this is the gold standard, if you like, of retaining wall design. Too big a topic to cover in this course, but the key thing to note is this requires a much greater confidence in your ground properties. You need to have a lot of knowledge about the stiffness of the ground, the strength of the ground, the stratification. It's a bigger buy-in to do the calculation. If you have a simple model and you have the wrong parameters, this will give you the wrong answers. So it is better if you've got the data. It's probably overkill on simple retaining walls because you just can't justify the time spent doing the more sophisticated calculation. There's a whole bunch of things you need to consider. Eurocode, I'm afraid, doesn't say very much about this. You need to be looking at numerical courses in order to get information about that. Okay, so that's everything that I have for you on the general rules for retaining wall design. I've covered earth pressure theory. I've gone through the methods of getting the earth pressure coefficients, and I briefly covered the calculation models that you would then use to implement that earth pressure theory. Petrus, do we have any questions?
Yes, we have some questions left from previous. Probably we can little bit discuss. There were a question about the how to derive this constant volume friction angle. Should we go for shear box multi-cycle test, or should it be ring shear, or should we use the correlations? What is the practice?
Okay.
For example, in UK.
Ideally, you would do a laboratory test, and you'd either do shear box or ring shear. So that is what I would recommend, and I would take samples deliberately to do that. I would always look at my correlations because that will give me a first estimate of phi CV. For sands, the values of phi CV fall in a fairly narrow range anyway, so your test is probably only confirming a value that you can guesstimate from the simple correlations. That's why the correlations are valuable. But yes, a measured value is always better than a non-measured value. But obviously, there's an expense attached to that.
Okay. Well, there is another question about the reliability of dynamic probing tests, and maybe you can say some words if we can use dynamic probing for identifying these crucial parameters, strength parameters for soils for retaining wall design.
Okay, so dynamic probing is a shallow investigation tool. And so its strengths are in giving you a numerical value of something in superficial deposits, which are often the deposits where the cone test and the standard penetration test don't give you very good data. So it's valuable because you can do it fairly cheaply, quickly, economically. The problem is the correlations from the measurements into parameters. That there are correlations, but they're not universal. They're very locally site specific. And so if you haven't got a good correlation, you're measuring something, but you don't know quite how to convert it. I'm keen on measurements because it's better than having nothing, but you do have to be cautious. I think you would need some conventional measurement of strength to check any correlation that you use is giving a sensible answer. And if it is, then you're laughing. If you don't get that tie-in, then you've got to be a bit cautious about it.
Okay, maybe last question before lunch break. About the soft soils. If we have soft soils, there was not much on the slides, but maybe you can briefly touch this topic because, of course, if we talk about soft soils, these effective parameters like friction angle, cohesion, and also interface friction could be problematic to obtain with in situ tests. And maybe you can tell a few words about the practice also in UK, and if we face, because, well, for example, in Riga, we are very often facing soft like organic silts or soft clays or even peats.
Yep. Okay. Well, peat is a problem. Okay. For soft clays, fine soils, quite often, I mean, I don't know the geology of Riga, I'm afraid, so I'm going from my standard knowledge of alluvial deposits, fluvial deposits, so things that haven't been heavily over-consolidated historically and sort of are there and haven't had a lot of preloading. Typically, there are reasonable correlations to get in situ earth pressure coefficients with depth and to get undrained strength with depth. There are fairly good correlations between vertical effective stress and strength. So on a lot of soft sites, you can make a reasonable estimate of the strength with depth, just knowing its geology if it's a soft soil. You might have a crust at the top where the soil has dried out, has been leached, where it's appears to be a lot stronger, but that may not be a reliable strength to use for retaining wall design, for example. So yes, it is difficult getting, well, I wouldn't necessarily use laboratory testing to get the parameters that you're talking about. I would probably use cone testing to give me the parameters and use correlations, and I would cross-reference with rules of thumb that I've got from the literature. Effective cohesion in the UK, we would ignore. We would not rely on it at all for retaining wall design, particularly in soft soil. So we just throw that away. And that's an extra little safety margin that we have. The wall friction, typically people are quite happy in the UK using 2/3 of phi, and we have no qualms in doing that. So it is really down to measuring phi. And obviously I've given you some formula for Ka and Kp for different values of phi. If you're getting undrained strength, say you can get it from correlations with vertical effective stress, supplemented with field tests is the way that I would go.
Okay. Well, is there space for last question? There is one more. Very shortly, maybe this is quite interesting question about the if we are using these continuum mechanic methods, numerical modeling. I mean,
yep.
How to apply partial factors in this case if we are using numerical models?
Okay, I skipped over it because it would take half an hour to explain.
Okay.
But there's two basic approaches. One is you apply your partial factors on the material properties at the beginning and then run your finite element analysis. There are some experts who say that's perfectly okay and it will give you a safe answer. I know other finite element experts who will say the danger with that is you get the wrong failure mechanism. And I know that in Imperial College, Professor David Potts has shown that for a footing, you can get completely the wrong failure mechanism, get the wrong answer from finite element if you do that. So it's not guaranteed to give you the right answer. Because of that, there seems to be a body of opinion that thinks that you should do your calculation without any factors at all, so basically a serviceability calculation, and stop the calculation at various points along the route, and then restart those calculations from those points with reduced material strengths. So the idea is you do a calculation at serviceability, your best estimate what's going to happen, the real behavior of the wall, and then at various points you let the wall, the ground, become weak magically, and you see what extra movement you get, and you then plot those points together. I'm not sure if my diagram showed that. Yes, it did. Bottom left diagram. The top curve is the unfactored characteristic calculation. That's the best estimate of load versus displacement. I save the calculation at points 1, 2, 3, and even 4. I go back to them and restart the calculation with different parameters for the soil, with the partial factors applied. Because I haven't changed the load, I get extra displacement. I then join the points up at the end points of those extra displacement, and I get the dashed curve. And that's sort of a quasi ultimate limit state low displacement curve. And if that is acceptable, then your design is fine. Now, in programs like Plaxis, that is automatically implemented for you using what is called the strength reduction method. So this can be automated. The devil is in the detail. But again, I think some reputable finite element programs do it very well. That is probably the best method at the moment. That is not to say that better methods won't come along.
Okay. I guess the rest of the questions we can leave.
Yes, I think we need to leave them to later. People need their lunch, so let's pick those up later. So in terms of where we've got to. So we'll take a break now. We'll resume on the hour, 2 o'clock your time, and I will then be dealing with verification, which is the details of how you check your design is going to work. See you in 20 minutes or so.